All right, so we're in section 5.5, and we're going to talk about the double and half angle formulas. Yes. This is the last thing. All right, so what I want to do is I want to start with our sum formula for sine. So the sine of u plus v, I'm just going to write it out, is sine u cosine v plus cosine u sine v. And instead of putting two different angles in here, I'm going to put u in twice. What's another way of writing u plus u? 2u. So this is the sine of 2u, and I'm going to write out my sum formula with a u in each place. So I get sine u cosine u plus cosine u sine u. So I get sine of 2u equals, and how can I rewrite this? I have sine u cosine u and another sine u cosine u to sine u cosine u. So there's my double angle formula for sine. That comes from my sum formula. So I can find the sine of 2 times an angle if I know the sine of the angle and the cosine of the angle. So this opens up some possibilities for solving some different kinds of problems. All right, let's write our cosine sum formula. Cosine of u plus v, cosine u, cosine v minus sine u sine v, and we'll write cosine 2u is cosine u minus sine u sine u. And so I can write that the cosine of 2 times an angle equals cosine squared u minus sine squared u. So that's one of our formulas for the cosine of 2 times an angle. If I know the cosine and the sine of the angle, I can find the cosine of twice the angle. I can also rewrite this one by using the Pythagorean identity, either for the cosine squared of u or the sine squared of u, and I can write this one in 2 other forms. So I would use the Pythagorean theorem on the cosine or the sine, the Pythagorean identity, to rewrite this. So I can also write this as cosine 2u equals 2 cosine squared u minus 1. And I would get that by substituting 1 minus cosine squared theta for sine squared. And I can also write cosine 2u. If I substitute 1 minus sine theta for cosine squared theta, I get 1 minus 2 sine squared. So those are 3 different forms of my double angle formula for cosine. They all come from the cosine sum, and these other 2 forms come from substituting for cosine squared u or sine squared u. And I can go through a similar process with the tangent. I would use a tangent sum formula, substitute u in twice, and I can write the identity or the formula for the tangent of twice an angle. I'm not going to go through the process like we did here, but it comes from the same place. So I can write that the tangent of 2u is 2 tangent u over 1 minus tangent squared u. And that one comes from our tangent sum formula. So each of these gives us a way to find the sine, the cosine, or the tangent of 2 times an angle if we know the sine, the cosine, the tangent of just the angle. Yeah, ma'am.
The bottom is
1 minus tangent, so tangent squared plus 1 is secant squared. So it's close, but not quite. All right, so questions on how we came up with these. So these come from our angle sum formulas. So nothing really new, just a slightly different form. So let's take a look at how we might use some of these formulas. And then we'll talk about the half angle formulas that come from these. All right. So we want to solve sine 2x. And I'm going to put this in parentheses so we know, so we're sure what we're talking about there. Minus cosine x equals 0. So we can't use our normal process for solving this equation because we can't factor. We have a sine of 2x and a cosine of x, so we're not only do we have 2 trig functions mixed, but one is 2 times an angle and one is just the angle by itself. So we need to do a little more work here. So here's where we're going to use our formula, our identity, for the sine of 2x. Sine of 2x is 2 sine x cosine x minus cosine x equals 0. That looks a little better now. So what can we do to solve this one? Factor. We're going to factor the cosine. So I'm going to factor that cosine x out. I'm left with 2 sine x minus 1, and that equals 0. And now we're home free. This tells us that cosine x equals 0, or if I set this equal to 0, I get sine x equal to 1/2. What values of theta give us, what values of x give us cosine of 0? Pi over 2 plus 2n pi, and what's the other one? Negative pi over 2, I could write negative pi over 2, or 3 pi over 2, I'll write that in parentheses. Either one works. Plus 2n pi. And how about sine x equals 1/2? X equals pi 6. And which other one? 5 pi over 6. So we were able to solve this equation by using our double angle formula for sine. So it just opens up a new type of equation, a new set of equations that we're able to solve for. Questions on that example? And I just want to go back here really quickly. This formula and these two, they show up. In my calculus class, we use them, especially now when we get into second semester, we use them very, very frequently. So these double angle formulas do show up quite a bit. So they are very useful. They might seem kind of a little bit out there, not particularly useful, but they are extremely useful. All right, let's look at another example. Questions? Everybody good with this one? All right. Another type of problem you might see is that we are given that the sine of x equals 12/13 and pi over 2 less than or equal to x less than or equal to pi. Before we write anything else down, what is this telling us? We're in the second quadrant. So all of our answers are coming from the second quadrant. This is telling us we're in the second quadrant. We want to find sine 2x, cosine 2x, and tangent 2x. So we know the sine of the angle. We want to find the cosine of the sine, the cosine, and the tangent of 2 times the angle. Well, let's start with sine. We know that the sine of 2x is 2 sine x cosine x. We know the sine of x. How can we find the cosine of x? Draw a triangle. Perfect. This tells us 2 sides of our triangle. We're in quadrant 2. So I'm going to draw my triangle this way. There's x. The sine of x is 12/13. So that's 12. That's 13. What's our missing side here? 5. And we're in the second quadrant. So this is a -5. If we didn't remember this was a 5, 12, 13 triangle, we can use the Pythagorean theorem to find that missing side. So the cosine of x is -5/13. We're in quadrant 2, so it makes sense that the cosine would be negative. Well, now we're set to find our sine 2x. Sine 2x is 2 times the sine of x, 12/13 times the cosine of x, minus 5/13. And when I multiply that all out, I get, this is a negative 120, 169. So there's sine of 2x. Now let's find the cosine of 2x. We have several choices we can make here. We have 3 formulas that we can use to find the cosine of 2x. We could choose any of these. We have the sine of x and we have the cosine of x now, so we could choose any of these. I happen to choose this one because we already knew the sine of x, so I just used the one that had what we knew. So I said, and I could choose any of the 3, we'd get the same answer. So the cosine of 2x is 1 minus 2 sine squared x. So I plug in my numbers, 1 minus 2 times 12/13 squared. When I square this, multiply by 2 and subtract from 1, I get that the cosine of 2x is negative 119, 169. And does it make sense that these would both have the same denominator? What's the denominator telling us? What do these two ratios always tell us? These are the sides of the right triangle. So this is the hypotenuse of our triangle with the angle 2x. So it makes sense that they would have the same hypotenuse. So there's my sine 2x is here. And let's find the tangent of 2x the easy way. What's going to be the easy way to find the tangent of 2x? Not even thinking of a formula. Sine of 2x over the cosine of 2x. Tangent 2x equals sine 2x over cosine 2x. and I just found both of those pieces. So that's going to be negative 120 over 169 divided by negative 119 over 169. And what am I left with when I do that division?
120 over 119.
120 over 119. I flip this one and multiply, so the 169s end up canceling. So there's the sine, cosine, and tangent of 2x, starting just with the sine of 2x, or the sine of x, sorry. I think that's kind of cool to be able to do that. Questions on that example? So there's a couple of ways that we would use these double angle formulas. Solving equations, finding trig functions of double angles. All right, last thing we're going to talk about in chapter 5 is half angle formulas. And for the half angle formulas, I want to start with our double angle formula. So I'm going to start with, let me go back here. I'm going to start with these two formulas. And we'll talk about the tangent one as well. But I want to start with the ones for the cosine. We know that cosine 2u equals 1 minus, cosine 2u is 1 minus 2 sine squared u. Now can we agree that this angle is half of this angle? U is half of 2u. That make sense? It's half as big. So I can rewrite this and say that the cosine of u, it doesn't matter what I call it, as long as I keep this one half as big. 1 minus 2 sine squared of u over 2. This angle is half as big as this angle. This angle, half as big as this angle. Just a different way of writing the same formula. Now I'm going to solve this equation for the sine of u over 2. So I add this to both sides, solve this for sine of u over 2. I get that the sine of u over 2, the sine of half an angle, is plus or minus the square root of 1 minus cosine u divided by 2. And the plus or minus we decide by which quadrant we're in. So if we're in the top half of our circle, if we're in quadrant 1 and 2, our sign is going to be positive. For quadrant 3 and 4, our sign is going to be negative. So I just rewrote this double angle formula that came from our angle sum formula and rewrote it as the sine of half an angle. I can start with our other version. Let me circle this in red before I do that. I can start with our other version of cosine 2u. We also said that cosine 2u is 2 cosine squared u minus 1. And I'm going to rewrite that using the same idea. Cosine u equals 2 cosine squared of u over 2 minus 1. And I solved this for cosine of u over 2. And I get that the cosine of u over 2 equals plus or minus the square root of 1 plus cosine u divided by 2. And the plus or minus we decide by which quadrant we're in. Quadrant 1 and 4, cosine is positive. Quadrant 2 and 3, cosine is negative. So there's our cosine half angle formula, which came from our double angle formula for cosine, which came from our sum formula. So all of these come from our sum formula. And I can go through the same process for our tangent formula, and I can come up with a half angle formula for tangent. Tangent of u over 2 is 1 minus cosine u over sine u. And I can also change that into sine u over 1 plus cosine u. So there would be my half angle formulas for tangent. Which come from our double angle formulas, which come from our sum formulas. And the thing that I remember about these is I usually remember our original version. I remember these and realize that one angle is twice the other. So that helps me remember. These aren't a separate thing. They're just kind of rewriting them in a different way. So questions on where these came from? All right, let's do a couple of examples of how we might use a half angle formula, and then we are done with chapter 5. Okay, so let's say we want to find the exact value of the cosine of 165 degrees. So what this is asking us to do is see if we can figure out how 165 degrees, the exact value is a hint that this has to do with the unit circle, how 165 degrees is related to an angle that we could find on the unit circle. Anybody have an idea? Yeah. Nice. So 165 is 330 degrees divided by 2. So what we're trying to find is the cosine of 330 degrees divided by 2. So we're going to use our cosine half angle formula. This is going to be 165 degrees is in which quadrant? Second. So our cosine is going to be positive or negative? Negative. So we're going to use the negative sign. Square root of 1 plus cosine of 330 degrees divided by 2. And the cosine of 330 degrees, square root of 3 over 2, so this is 1 plus square root of 3 over 2 over 2. And if you left your answer written like this, I would be fine with it. We could simplify it and simplify it a little more, not really that much. But if you left your answer written like that, I'd be fine with that. So this problem asks us to recognize that 165 is 330 degrees divided by 2. We're in the second quadrant, so our answer is negative. All right, questions on that example? Okay, let's use a half-angle formula to solve an equation. So we want to solve 2 sine squared x, or 2 sine squared of x over 2. Equals cosine x. This is similar to the last one we worked on, where we had a double angle and a single angle. Well, here we have a half angle and a single angle. So we're going to substitute our formula for sine of x over 2 into this formula, into this equation, so we get everything with the sine or cosine of a single angle. So I'm going to substitute in for sine of x over 2. So this is 2 times plus or minus the square root of 1 minus cosine x divided by 2 squared. This quantity is the sine of x over 2, and I have to square that whole thing. And that equals cosine x. What does the square do to the square root? Cancel it. And if I have a positive or a negative and I square it, I always end up with a positive. So I don't have to worry about this plus or minus. So I end up with 2 times 1 minus cosine x divided by 2. That equals cosine x. Now we're almost done. What happens with these 2's? They cancel. So I get 1 minus cosine x equals cosine x. And that looks like a much nicer equation to solve. So what do I do to solve this? Add cosine. So 2 cosine x equals 1, or cosine x equals 1/2. Now we go to our unit circle. X equals, where is cosine equal to 1/2? Pi over 3 plus 2n pi and which one? 2 pi over 3? Is that right? No. That would give us a negative 1/2. So we could say negative pi over 3 plus 2n pi, which is also negative pi over 3 is the same thing as writing 5 pi over 3. So we go from this kind of intimidating looking equation to a pretty easy equation using our half angle formula. Questions on that example? All right. Homework. All right, there you go.